Everyone, thank you for coming. My name is Gabriel Mindlin. I'm one of the organizers of this school. Of course, you know, this is a school which is a preparatory school for this conference that will be held next week in Buenos Aires, which is StatPhys. StatPhys is a very important conference in the field. It has a very long tradition, and it is the first time that it's taking place in South America.
No, second time.
It's the second time.
Yes, it was. The first time was in Rio de Janeiro.
In Rio de Janeiro. In which year was that?
1999.
Okay, but since then it hasn't been in South America. It's a great opportunity for those of you that will attend to meet first-class researchers in the field, and that's the reason for which we considered that it would be appropriate to have courses on some of the basic subjects that are mainstream in statistical physics these days. As you see, there is a long list of topics that covers multi-agent dynamics, nonlinear dynamics, biophysics, and we're going to be trying to cover some of these subjects in this preparatory school. So the idea is that it is a school. So although we're going to be talking about our research, the main goal of this is to give space for basic questions and discussions. So we prepare classes, we prepare content, but the best that could happen to us is that you interrupt us as many times as is necessary, so we don't have a minimum amount of material that we have to cover. So please feel free to really interrupt us whenever you feel that you are interested in something, or we're going too fast, or there is something that you always wanted to learn. There are going to be, the structure of the school is, there are going to be 3 courses by myself on basic nonlinear dynamics, by Pablo on multi-agent dynamics, and Mauro Copelli in critical dynamics, which are 3, I would say, philosophically 3 important pillars of what is modern statistical mechanics. And then we're going to have on Thursday and Friday special lectures by Bill Bialek from Princeton talking about biological physics. And then we're going to have courses on multi-agent dynamics by Maxi San Miguel. But again, especially on these courses, please interrupt us as many times as you feel necessary in order to feel comfortable with the material. So it's the basic material which is part of the mainstream in statistical physics nowadays. Of course, we want to thank the ICTP for the help in the organization of this course, and FAPESPI and all the funding agencies, and all the staff from the Institute who have been very helpful, and I hope you have a great stay with us this week. So you are going to be asked, besides these lectures, there are going to be some guided activities. The guided activities basically are going to be presentations prepared by you on some posters and on some papers that we selected and that we posted in a web page, which you'll have to track. It is the web page of my nonlinear dynamics course in Buenos Aires, which is a page that I could edit, this past week. So if you go there to the web page of my course, there is going to be an entry which is papers for StatPhys 2019. So go there, and this afternoon we're going to start the selection process. You will make groups of 4 students each group, and you're going to be selecting today with your classmates, you're going to be selecting a paper, you're going to be asked to discuss it, and then there is a free format. You can make a presentation on the paper and explain to us the basic results. You can discuss how to frame it in the framework of contemporary research in statistical physics, or if you are more familiar with the material, you can reproduce a result, do some simulations, and incorporate some of your own creation to the subject. So this afternoon we're going to meet after the classes. We're going to meet in the first floor where there is space with tables and so on. Mauro, Pablo, and myself are going to be around. You are going to build your group. Okay, you're going to team up with 4 teams of 4. You're going to be selecting a paper. You can talk to us about it. If you're already working for your PhDs, maybe you can select something close to your own research or some of the papers. The authors of some of the papers are going to be the plenary speakers of the conference, so if you want to approach them, it's a great opportunity to study their latest work and be prepared for meeting with these researchers in the school. Okay, so I thought that the best way to present the subject of statistical physics is going back to the first chapter of the first volume of Feynman's Lectures in Physics, where he has this very charming comment where he says that if in some cataclysm all of scientific knowledge were to be destroyed and in only one sentence has to be passed to the next generation of creatures, what statement would contain the most information in the fewest words? I believe it is the atomic hypothesis that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are little distance apart, but repelling upon each, being squeezed into one another. In that one sentence, you will see there is an enormous amount of information about the world. It's just a little imagination and thinking are applied. And that's basically the program that, if you want, Gibbs was doing to build this bridge between the phenomenological observations of thermodynamics and the basic knowledge of how little particles interact with each other. And if you want, modern statistical physics deal with similar questions, but with units that behave in a little bit more complex ways. So for example, behavior in the animal kingdom emerges from the activity of spiking interacting neurons. Or when you want to study the dynamics in modern society, people try to model them in terms of the interactions between agents. So many issues that people are investigating, and these are just 2 examples, but many issues that people are investigating in contemporary statistical mechanics deal with the interaction between units which are out of equilibrium and are ruled by nonlinear equations. Let me give you an example of what I'm talking about. I'm going to be showing you an image that is taken by a microscope that detects calcium waves in the brain of a bird while the bird is singing. So I have a problem with sound here. I will fix the sound for the second part of the lecture. But maybe you were listening to, maybe you could listen to the bird singing, and while the bird was singing, what we were seeing was the activation of these neurons. So neurons are these cells. I don't know how much you know about the biology of the nervous system, but basically the nervous system is organized in terms of cells, where there are a set of channels that allow the interchange of ions with the medium, and whenever you have this spiking activity, you communicate information between these different units. That happens at the level of the brain, and then that is transferred to the periphery of the animal, and behavior emerges. So the question in this case is, again, how does that happen? How do you go from neural patterns in the brain to behavior? Because the generation of behavior, for example, the generation of song, requires the fluctuations of some motor gestures, like the air sac pressure or the muscle activity in the vocal organ, and sometimes very simple. For example, it can be periodic. When the bird is singing and you hear a syllable that is repeated one after the other, okay, there is some periodic behavior that emerges out of the interaction between millions of neurons, okay? So all this very simple behavior, maybe that allows you to do some very simple behavior, like moving your legs and just walking, emerges out of the interaction between these millions of units. So you have a very complex nervous system built by highly interconnected units, which are the neurons, and that eventually, in some conditions, give rise to very low dimensional dynamics. So this transition between these millions of interacting neurons giving rise to very low dimensional dynamics is one of the many questions that can be addressed or are addressed in contemporary statistical mechanics. So we have one problem, which are the units. The dynamics are ruled by nonlinear equations. Okay, these very interesting subjects that modern statistical mechanics is studying. Typically, the basic units have dynamics which are ruled by nonlinear equations. So one of the questions that we're going to be addressing is what kind of behavior can be expected out of a nonlinear rule. And then there is the question of interaction. What behavior can emerge out of the interaction between these nonlinear units? So in this particular course, in my course, we're going to see first a review of basic nonlinear dynamics. And in a second lecture, we're going to be trying to compute and see the efforts that are being performed in order to compute analytical calculations that allow you to compute the dynamics of variables that describe collectively those ensembles of many interacting units. So the first course is going to be today, and the first class is going to be basic nonlinear dynamics. The second one is going to be a little bit of applications. The second lecture also will have a first hour of pure calculations, how to do calculations on ensembles and compute equations for the order parameters, and then we're going to see experimental applications of that concept. So let's start with nonlinear dynamics. And again, how many of you are not physicists? How many of you come from different undergraduate background? Okay, and which is your background? Math. Biology? Biology? Mathematics? Okay. So for those of you in mathematics, maybe not so much. For those of you in biology, please stop me. I'm going to be reviewing a little bit of basic classical mechanics. So whenever you feel like, please stop me. So the origin of dynamics, and in some sense modern dynamics, is Newton, of course. And we are all familiar since the first course in undergraduate studies of Newton's equations. Basically, what these equations tell you is that if you unveil the acceleration everywhere in your phase space, basically you need some finite amount of information, and you can predict the behavior forever, because you measure a finite amount of information, the position and the velocity at an initial time, and then you can update the new position because you know the velocity, and the new velocity because you know the acceleration everywhere. And now that you have updated your variables, you can repeat that over and over. So whenever you have a Newtonian paradigm, you measure a finite amount of information, and you have your behavior described forever. Of course, the key in this is hidden in the third law that tells you that the forces that are implied in Newton's descriptions are these forces for which action and reaction holds. That means that the interaction takes place in one particular point, and there is no delay. So the rate of change of the variables depends on the exact value of the variables at that particular time. So systems with delays, for example, for which the third law doesn't apply, are excluded from the Newtonian paradigm. So when Newton came up with the idea that you have to measure a finite amount of information and the evolution of the system is unveiled forever, our expectation of what the natural law is changed forever, and changed for every discipline. So for example, when Hodgkin and Huxley in 1950 unveiled the equations that rule the dynamics of the voltage across a membrane, or the fraction of channels that are going to be opened, he's writing how the variables of the problem, the rate of change of those variables, change as a function of time, as a function of the value of the variables at that time. And that is a Newtonian paradigm. Although there is no acceleration, there is no force, but basically the concept is the same. You don't have to find, which is the whole history of a problem. You just have to measure the values of the, the variables at one particular time, and the future is unveiled forever. Okay? And that is what we call a Newtonian paradigm, to describe the dynamics of a problem in terms of a finite set of ordinary differential equations. So that was great and changed our expectations of what a natural law should be forever. But then Newton put us in a labyrinth, put us in a place which was very difficult to get out from, which is the following. So you remember from your classical mechanics, those of you who are from physics, when you studied the two-body problem, there was this great tool. Because of the conservation of momentum, you know that the motion is going to be taking place in a plane. You do this polar description of the motion, and then when you arrive to the equations that describe the behavior of a variable that is 1 over the position, you reach that the solution of that variable, of the equation that rules the dynamics of that variable, is basically the harmonic oscillator when the force is 1 over r squared. So Newton can solve the two-body problem, if you remember from your basic classical mechanics course, analytically, and you can compute analytically the equations of ellipses and parabola and so on. And that put us an expectation of what is to solve the problem in physics, which is to find the analytical equations that describe the motion. And that paralyzed physics for basically 200 years, because when people tried to do the next complicated problem, which is the three-body problem, that is something that you can no longer do. So the problem of classical mechanics is that it was set up by Newton conceptually very clearly, but he also solved the problem which put our expectations maybe a little bit too high. So 200 years later, Poincaré said, the exit is not to be smarter in terms of the calculus, but to use geometry, topology, and qualitative descriptions of behavior to understand what is the meaning of a differential equation. So the modern idea of nonlinear dynamics is to look at the problems not from the point of view of solving analytically the equations, but doing some geometry and a geometrical description. Let's see what I'm talking about with an example. This is the simplest dynamical system that you can imagine. It's one-dimensional, okay? So it's a one-dimensional differential equation. You only have to measure one initial condition, and the behavior is ruled, forever. And in this case, we can analytically solve this equation. We know that there is only one fixed point, which is at 0, unless A is equal to 0. In that case, there is a degenerate subspace of fixed points. But unless there is this degenerate case, then you have only one fixed point, which can be unstable or stable depending on the sign of A. So you can work out the analytical description. That's perfect. But you can also study the one-dimensional phase space, which is X, and plot in an auxiliary axis, which is the derivative. In this case, it's going to be the straight line AX. And then there's going to be only one fixed point. And the only possibility is to have only one fixed point or an infinite set of fixed points, a degenerate subspace. That's the only thing that you can find in this one-dimensional linear problem. But as soon as you introduce a nonlinear equation, this is the logistic map, the logistic differential equation, then the dynamics gets more interesting. The phase space, that means the space of the variables which are deterministically prescribed by your differential equation. This is a one-dimensional differential equation with a smooth vector field. So when you have one initial condition, the solution is unique. Now, the dynamics is more rich because if, again, you plot this one-dimensional phase space, and in the vertical axis you plot the derivative of this variable, what you have is that this nonlinear function can intersect the axis in 2 points. So you can have 2 stationary points. Stationary points means the points where this vector field is 0. That means that the derivative is 0. And that means that if you put an initial condition there, the system stays there forever. So fixed point means this equal to 0. And this equal to 0 for a nonlinear system can have more than one isolated fixed point. So when you talk about a nonlinear system, of course, because of all this hype and so on, we think that we're talking about very complex dynamics. The first thing we have to think about is coexistence of stationary solutions are now possible. So if in biology this is a very known system, if you forget about this will be the way in which a population growth, depending on the rate of birth of this population. And this correction is a correction that says that, well, yeah, eventually you can have a rate of growth of a population that depends on the value of the size of the population. So instead of being a constant, it's going to be something that decreases if x increases. So this could be describing the average size of a population where the effects of overpopulation are included. And what it's saying that in principle, even if A is positive, you don't have an unbounded growth of the dynamics. If you grow beyond some point, then what you're going to be falling is to some finite population value. So in terms of this geometry that I was describing, what do I mean? That in this case, also, it is possible to find the analytical equation that rules the dynamics of the variable x. You can do that. But modern dynamics looks for qualitative arguments to say what is the qualitative dynamics. For example, in this case, you will say, well, since the derivative of the variable is positive in this range, for all the variables that are between 0 and 1, the derivative will be positive, and therefore any variable here will tend to grow. And here, since the derivative is negative, the value of the variable is this, the derivative is negative, and therefore you will be decreasing. So you will make arguments about what is the dynamics just by looking at the geometry of phase space and the qualitative behavior of the vector field that is ruling the dynamics. So far? So far you're bored. Okay. So now, a key concept in nonlinear dynamics is the following. The concept of bifurcations. Now that you know that you can have this richer behavior in phase space where you can have many isolated points, one thing that will happen is that when the parameters of the systems are changed, you can have qualitative changes in the solutions of the problem. So whenever you have a qualitative change in the set of solutions of your problem, you're talking about a bifurcation. So for example, in this case, if the vector field, if this equation, which is nonlinear, has a parameter that is r, if r is positive, and if we plot the phase space and the derivative here, what we're going to have is the vector field never intersects 0, and therefore the dynamics is always growing. But then when r is equal to 0, you have the possibility of having one fixed point. And if r is smaller than 0, now out of nowhere, now you have two isolated points which are coexisting, one which is unstable and one that is stable. So this dramatic change from going to no fixed points to going to two fixed points, one stable and one unstable, is a typical phenomenon in nonlinear physics, in nonlinear dynamics, and it's called the bifurcation. This is the typical plot of what is called the bifurcation diagram. You plot now the fixed points as a function of your parameter, and you see that there are two different regimes. One for which there are no fixed points, and one for which there are two fixed points. And the scaling, if you are approaching this parameter, the bifurcation, is very specific, okay? The fixed points scale like the square root of minus r. So this is called the bifurcation diagram. Now, a myth that was against nonlinear studies was that whenever you are going to be working with a nonlinear equation, your world is going to be completely different depending on what that equation is like. So for every equation, you will have a complete different world, complete different scenario. This doesn't happen. So for example, in this case, you have a one-dimensional equation where the vector field is minus x plus this sigmoidal function. So this sigmoidal function is a step function. It goes to 0 when x goes to minus infinity and goes to 1 when x goes to infinity. And depending on the value of rho here, okay, this inflection point can go from left to right. So if rho is negative, it's going to be to right, to left. When rho is negative, it's going to move to the right. So if you're interested in looking at the fixed points of this problem, that means the points at which the vector field is 0, then you have to intersect x with the sigmoidal. And therefore, you can have one scenario, depending on your parameters, c and rho, where this happens only at one point, that is this one here. But eventually, if you start to decrease rho, what you're going to be having is that this sigmoidal function moves to the right, and eventually, now you will have two additional intersections. Of course, if C is high enough. So out of nowhere in this region of phase space, you're going to have now two additional fixed points. And if you move farther, what will happen is that these two will approach together, and eventually, when this moved to the right enough, the only fixed point that will survive is this one here. Why am I showing this particular problem? Because although this is a vector field that you probably never saw in your life, and you will never see again after this class, this qualitative change of having these new two fixed points, or the disappearance of these two fixed points, is the same phenomenon that we saw before when we studied the equation with a quadratic term. The appearance or disappearance of two fixed points is exactly the same. We're going to go back to this in a minute. So the idea is that there are going to be minimal vector fields, minimal problems that you can describe, and that will capture important aspects of your particular nonlinear problem. So when we're talking about caricature models, like the ones that we're going to be having in the class later in this week, think of them not as toy models which represent nothing, but as models which can be representative of important classes of problems. Okay, here is a typical plot in which you summarize the results of a nonlinear problem. It's called a bifurcation diagram. In this case, there are two parameters in the problem, okay, which are rho and c. And therefore, typically what you do is you represent in this two-dimensional space all the qualitative regions, all the regions in parameter space where the dynamics is qualitatively different. So as we said, in order to have this these three intersections, this sigmoidal had to be sharp enough. If C is very small, and this very slowly grows from 0 to 1, then it doesn't matter where you are, you're going to have only one intersection. But you have to be steep enough in order to be able to have three intersections. Therefore, in your parameter space, you're going to have that C has to be large enough so that there is a regions of rho values where you can have three fixed points. If C is sharp enough, then you're going to be having only one fixed point. What happens in this line? Well, in this line is where you meet two of these fixed points that are about to appear, and in this line, you have these two fixed points that are about to appear. So these are bifurcation lines. So typically when you have a nonlinear system, your basic objective is to sketch or draw your bifurcation diagram. So that will organize all your simulations, that will organize all your study. You don't have to search in parameter space like crazy, but you have to find where you will have qualitative changes. Those are going to be the bifurcations. And then you have to divide your parameter space in regions where then the dynamics is qualitatively different. Of course, this is all a whole course on nonlinear dynamics in 1 hour, so I'm just giving you the headlines. If you want to do any calculation in particular, you will be referred to particular references and bibliography, or you can ask us during this week. So far, how are we doing? Perfect. Questions? Will you give me a break so I can drink a water with a smart question or a silly question, whatever kind of question? We're still shy. Well, no problem. Okay, let's continue a little bit more. So when you have in a linear system, the dynamics is organized not only by the structure of the vector field, that means by the structure of this function, but of course by the topology of the variable. So what I'm showing you here is something that we'll need for the second class, actually, for the class on Wednesday, which is a dynamical system that is one-dimensional, but X does not belong to R, it belongs to S1. So X is a phase, okay? So X dot is equal to omega minus the cosine of phi. So you have your phase space, which is the circle here, which is a circle. But basically, notice that if omega is larger than 1, you will never have that this vector field reaches the value of 0. Omega minus cosine of phi, if omega is larger than 1, is going to be always positive. So the dynamics will be that the derivative of this phase will be always positive. So the system basically is going to be going around. So that's the only thing that will happen. Of course, it's going to be going around, but not harmonically, because if the vector field was x dot equal to omega, that would be a harmonic oscillation, right? But this is not harmonic, because whenever you are close to 0, the vector field is almost 0. Therefore, when you are going around here, you are going around at an uneven space. You're going to get stuck in 0, and then you're going to escape. You're going to get stuck in 0, and you're going to escape. Okay? So whenever you are close to 0, the vector field is going to be almost 0, and therefore x dot is going to be almost 0. But of course, it's not exactly 0, so you keep on going. So what you're creating is an oscillation, which is periodic, but it has a very strong spectral content. It's going to be harmonically very, very, very thick. You're going to have like spikes, like real spikes. Now, if omega is smaller than 1, then you can have an intersection between the cosine of phi and omega. Okay, so if omega is smaller than 1, what you're going to be having are two fixed points, which appear out of the blue if you want. Okay, so there is, again, a saddle node bifurcation, like the one that we studied before. Locally, it is the same as the problem that we studied when we saw the equation x dot equal to r minus cosine of x. And now you're going to have that this point is a stable point, and this point is an unstable point. So for the people in biology, you can be in this stationary point, and if you perturb it a little bit, then you're going to be going back to this point. You perturb it a little bit more, and then you come back. You go this way, and again, you come back. But if you perturb it above a threshold, what will happen? You're going to be expelled, and you're going to be making a huge excursion of the phase space. So instead of your perturbation leading you back to this fixed point, you're going to be having a huge spiking before you go back to your fixed point. Does it remind you of anything? Of what? That's right, the spiking of a neuron, okay? This regime is called excitability, okay? It's a regime where you have a stationary state, but there are two different ways of returning to the stationary solution. So it emerges out of the interplay between a local bifurcation and the topology of the phase space. By the way, this is a way of generating oscillations, but imagine, in this point, the system is not oscillating. Then you change your parameters, the system is still not oscillating, and then you move your parameters, and a solution appears. But this solution will appear with a finite amplitude and infinite period. So if you plot what happens with the period as your parameter is further increased, what you're going to find is that you have this behavior where if you approach from positive omega larger than 1 to 1, the period explodes. So this is a way where you have one oscillation being born with infinite period and finite amplitude. And the scaling is going to depend on some local properties here. We're going to be discussing this further in a little while.
Sorry,
See.
if you go back.
Sure.
I didn't understand, although I understood this, what really happens at this graph on the left.
Here?
There is two stable points. One is...
No, one is stable, the other one is unstable. Okay, so what happens is the following. So what you have is your vector field F is omega minus cosine of phi. So if omega is 0, what you will have is, let's see. This will be pi. This will be pi over 2. This will be 3/4 of pi. This will be 2 pi. This will be for omega equal to 0. Now, if omega goes to 1, okay, and then you have these two fixed points. In omega equal to 0, you have these two fixed points. Here, since the vector field is positive, so you have this, and now you have this. Here, the vector field is negative, so the dynamics is returning here. Now, when omega starts to grow, okay, what you have is that these two fixed points get closer together. So you have one unstable point here, one stable point here, and they're approaching together. When omega is beyond 1, these two disappear. Okay? That's okay? Great. So locally, this is very similar to what happened, of course.
I understand one precise point. Why that one is unstable?
You're inheriting this. You're inheriting this. Imagine that in this point in here, you have that the vector field in this region is negative, and all over here is going to be positive. So this point here is unstable.
Yeah, but why you don't go around and...
You do. So what happens is the following. Locally, it's unstable, but the system has an attractor. So what happens is that if you perturb it locally, you're going to be expelled. But of course, globally, then you end up in the other fixed point here. Okay. So it's not a bistable system. It's a system that has only one stable point and one unstable point. So in your phase space,
So you are on S1, right? You have a S1 space.
exactly. So that's the reason for which I said that you have to take into account the local dynamics and also the global topology of the variables.
Okay.
So in this case in here, what you have is that this is the attracting point. This is the repelling point. If you perturb it, I'm doing this right? Because it's minus cosine. Thank you. It's minus cosine. The concept is the same, but thank you very much. Yeah, thanks.
But I got it.
But you got it, right? So you're in this attractor, and then if you expel it backwards, you go like this. Yeah, thank you. It's minus cosine. So should I correct it, or it's...
No, it's fine. I got it.
Okay.
Sorry.
Perfect. Any other question? Okay. Let's continue. So what I was describing to you when I was saying that this bifurcation locally was the same as we discussed previously, is that if we now do a Taylor expansion around x equal to 0, okay, you can find that the vector field can be written basically as the vector field that we studied before. So it's just quadratically. The vector field behaves in a quadratic way. There is a whole chapter in linear dynamics that deals with the problem of how to go from your particular problem to the simplest paradigmatic equation that captures the basic dynamics. This theory is called normal form theory. But again, this is not the scope of this particular course on how to go from a system that linearly behaves in some way, how to go to the normal form. There are complete courses on linear dynamics on that. But the idea is that, again, when people are going to be talking to you of very simple model, keep in mind that not necessarily that means a toy model which has no pertinence. It can be simply that they are talking about the normal form of the equations by which they are describing the dynamics of the particular units. So the normal forms are simple vector fields that can be obtained algorithmically, in this very simple example by doing Taylor expansion, and are representative of a large class of systems. Okay. There are different normal forms. And one of the interesting things about the normal forms is that they are algorithmically. So you can classify them. And again, we're not going to do them here. But I'm going to show you some representative dynamical systems in one-dimensional vector fields that have qualitative different dynamics and that correspond to different normal forms to let you see what kind of different behavior you can have. This describes a qualitative change in the linear part of the vector field, which is described as a transcritic bifurcation. And in this case, the vector field is Rx minus x squared. If you plot this vector field, you have this thing here. If R is equal to 0, you have this vector field. If R is smaller than 0, you have this vector field. So if you look at the bifurcation diagram, that means the fixed points as a function of your parameters. For negative values of R, you're going to have two fixed points, one stable and one unstable. And then at 0, what happens is that you interchange stability. Okay? So basically, you are having that your system is has an attractor in the variable equal to 0, and then suddenly it's turned on. For example, if you look at the simple laser model, the simplest laser model that you can have, then it's turned on as a transcritical bifurcation. And the scaling, which is the way in which you can recognize the bifurcation, is very specific. The amplitude scales linearly with the change of your parameters. This is another interesting case. It's called the pitchfork bifurcation. The pitchfork bifurcation is described as a vector field which is highly non-generic. It doesn't have a quadratic term. It has only a cubic term, but that implies that this equation is equivariant when you have a reflection. So you have a symmetry in this equation, which is that the equation remains the same if you change x by minus x. If you plot the vector field, you have that the vector field is mu x. That means locally it's like a straight line. And then for large values of x, it's going to be behaving like x cubed, like minus x cubed. Okay? So the vector field is this. So now in this case, yes, we do have the B stability. Okay? You have the possibility of having this attractor or this attractor if mu is larger than 0. And 0 is going to be a repulsor. Of course, if mu is negative, you're going to have a vector field that goes like this, okay? And then you're going to have that this one here is going to be an attractive point. What I was describing is this. Again, the equation has a symmetry, which is that it remains the same when x changes by minus x. And this is interesting. When you change your parameters, you can go to a solution that has less symmetry than the differential equation. That phenomenon is called spontaneous symmetry breaking. That means when you have your solution, when you have your problem has a symmetry, has a reflection symmetry, and that doesn't change, never. But when you change your parameters, your solution, which was stable, suddenly loses stability, and you go to either one solution or the other one. So now your solution will have a smaller symmetry than the differential equation. When that happens, when your solutions have less symmetry than the differential equation, you talk about spontaneous symmetry breaking. Why spontaneous? Because the problem keeps on being symmetric. It is your solution, which is one of the two. So the set of solutions is symmetric. You have two solutions which are symmetric conjugates, but you go, depending on your initial conditions, to one or the other. This is opposed to the concept of external symmetry breaking, where eventually you have something like this. You have a problem which is symmetric, and then eventually you perturb it externally, and now your solution has a little bit less symmetry than the one that you had at the beginning. So now your problem, instead of being described in terms of bifurcations, okay, stationary solutions as a function of mu by a system like this, depending on the values of epsilon and so on, will become something like this. In a problem where you have an imperfect symmetry, then if you keep on moving your parameters, you are biased to continue by the, in the region where your symmetry was externally broken. But eventually you can overcome that and go to the other solution. One example, we were paying with our credit cards yesterday with Pablo, and this is a good example. As you can see, my credit card is bended because I usually use it like this. If it wasn't bended, okay, and I push it, longitudinally, this problem would be symmetric. I'm pushing in this direction, the credit card is symmetric, and I push it, and eventually when I reach some value, I can go either like this or like this, okay? Now, since this is already bended, whenever I push, I will always go to the region where I have my bias. So I keep on moving my parameter, and instead of jumping to either side, I will go preferentially to one side. But of course, if I push it and I put my initial condition large enough, I can bend it to the other way. Okay? So this is the difference between a spontaneous symmetry breaking and an external symmetry breaking. Of course, the final result will be that for some values of your parameter, you will end up with a solution that has less symmetry than your original problem. Okay. So far, we've been talking about one-dimensional dynamics. How does a low-dimensional dynamical system arise in a natural science problem? Let me take a little bit of water and another question. Can be a friendly question. Yes, thank you.
If I understood correctly, the perturbation leads to the external symmetry breaking.
Right. If you perturb the system here, now this equation will no longer be invariant under the change of x to minus x. So when that happens, is that you have an external symmetry breaking. And the spontaneous symmetry breaking deals with the problem that in an equation that keeps on being symmetric, depending on your initial conditions, you go to one of the two solutions that has less symmetry than the differential equation. But of course, in this problem, if you go to one of those solutions, there is another symmetric conjugate to which you could go if you put the right initial conditions. Some other questions? One of the wonderful things about these schools is that we are basically not going to be seeing each other probably ever again. And you won't be seeing each other ever again. So we can ask the most crazy questions. No one is going to give a shit, really. So we can be really friendly and ask whatever we want to know, and not worrying about
What happens if you take x as imaginary?
Okay, then if you are increasing the dimensionality of your problem, and that becomes a completely different problem where you have more rich behavior. And we're going to see complex equations in a little bit, if you bear with me. But that would change completely your scenario because the dimensionality of your phase space will change. Here. Okay. I will explain it with detail if you repeat, Herman, your question a little louder.
If you could please repeat how is that how is the spontaneous symmetry goes?
Okay. So, the first thing is to identify when you have a symmetry in your equations. So you have an equation, and what you're wondering is which is the set of transformations on your variables that leave your equations in the same shape. So you have dx mu x minus x cubed, and then you say, if I change a by x by minus x, what happens? I will have this. Minus 1 to the cube is equal to minus 1. You have this is minus 1, and this is minus 1. So basically this says that when you change x by minus x, your equation is invariant. So you have a symmetry in the differential equation. Now you study the fixed points of this. What you have is that if mu is smaller than 0, you have something like this. And in this case, what you have is that the vector field for negative x is positive, so you have that your variables are growing. And when x is positive, f of x is negative, so the variables are decreasing. So whenever you're looking at the stationary points, whenever mu is smaller than 0, you're going to have that 0 is a stationary point. So in here, your fixed point, your stationary point, is symmetric, just as your differential equation. Your differential equation is invariant to the change of x to minus x. And since this is 0, that happens to this stationary point. Now, when mu is positive, what you're going to have is that the vector field fx is something like this. So now, this point is unstable because you go in this way. And for x smaller than this point, the system has negative derivatives. Which are these points? These are the points where this is equal to 0. I take x common factor, and you have mu minus x squared. That means that we're talking about the two solutions which are plus or minus the square root of mu. That means that these two are conjugate solutions. This is square root of mu, and this is minus square root of mu. That means that each of these solutions now is not symmetric, because if you apply x to minus x to this solution, you go to a different solution. And this solution goes to another solution. So the solutions that are born in these bifurcations are each of these non-symmetric, because are different from 0. This is square root of mu. This is minus square root of mu. This one is symmetric under the change of x to minus x, which is the unstable solution. But the two solutions to which you can go, either one is a completely non-symmetric solution. So you have that your problem kept on being completely symmetric. The setup is symmetric. The equations of elasticity of your card is symmetric. The equations of the elasticity, the external form, everything is symmetric. But you went to one of the two solutions, which is non-symmetric. When that happens, you talk about spontaneous symmetry breaking. Is that more clear now? Thank you for the questions. Okay, so one-dimensional dynamics, very simple dynamics. Why to care about that? Well, it is a very important aspect in nonlinear dynamics to talk about the relative importance of the different timescales, which is at the core of the effective dimensionality reduction of a dynamical system. Let me give you an example. So this is a very simple example where you have a physical pendulum. So this is the gravity term of a physical pendulum. So I'm applying external torque. And maybe I have a little spring here, okay, applied also to this bar. In order to apply the torque, what I do is I put my physical pendulum in a tank with oil, and I'm making the tank go around. And that applies an external torque to the bar. Okay? Someone wants a better description of this mechanical problem? It's kind of artificial, but you know. So a physical pendulum, everyone understands that? Yes? Okay, this is a torque applied to the pendulum, and this is a restitution constant by some spring attached to the pendulum to this axis in here. Anyways, it's a two-dimensional differential equation, typical equation that comes up out of studying in a Newtonian framework in a mechanical problem. Now, let's analyze the dynamics of this problem by first scaling the time. So I'm going to be choosing the scale that I use to describe the time. So I put like a scaling the time, which is t. So whenever I take a derivative, so my time t is going to be some scale times and a dimensional unit of time. So whenever I take the derivative, t goes down. And if I take a second derivative, t squared appears in the denominator. So my differential equation in this adimensional time is going to be this. Now, there is going to be a variety of regimes depending on the relative size of the parameters. Typically, one would say the inertive term, the inertia, is going to be not important whenever this mass is very small. You'll agree with that, right? If this mass is very small, the Newtonian term with the inertia is going to be not important. The only problem is that if you want to do it in a silly way like that, is that also the vector field has the mass. So you have to be a little bit more careful when you want to talk about the importance of the inertive term, because you cannot say that m goes to 0. M goes to 0 also eliminates the very effect of gravity. So in order to see when the second derivative or the first derivative is more important, what you have to do is to work carefully and compare the coefficients of the term with the first derivative and the terms of the second derivative. So eventually, you can find a regime where, for example, if I choose the parameters so that b over t are equal to mgl, that means I choose as a time scale b over mgl, then this inertive term will not be important as long as this thing here is much smaller than the parameter that I have in here. So if L over G over T squared, that is this, is smaller than this, which is equivalent to this condition, that is the mass is small, but not goes to 0. The mass is small compared to a specific ratio of the dissipation and the length and everything else, then I can neglect this term in here, and I end up with a one-dimensional equation. In terms of the phase space, imagine that now we have a two-dimensional phase space problem. So my second derivative, what I'm talking about is the following. If you have a second derivative problem, like your harmonic oscillator, that can be transformed into a set of finite first-order differential equations by describing that dx at dt is equal to y, and dy at dt is equal to minus omega square x. So a second-order differential equation is equivalent to a set of two differential equations of dimension 1. So what I'm doing here is rewriting the differential equation that we had at the beginning. D omega d tau is equal to omega, and d omega d tau is equal to one parameter times all this. So what happens is that dynamically, and of course now the dynamics is described in a two-dimensional phase space. I have to have one point in my phase space to have a unique future that is described by the integration of these equations. So now what happens is that if my parameter here is very large, that means if epsilon is very small, the dynamics of tau will be to, for example, if you are with these values larger than 0, if you are above this curve, if epsilon is very small, you're going to collapse dramatically fast, okay, to this region where this is equal to 0. And when this is equal to 0, then you're going to slow down. So basically what happens is that your dynamics is going to be to collapse incredibly fast to this curve in here, which is the curve where this is equal to 0. Now, this curve is equal to 0 is minus omega plus all this equal to 0. That means that since omega was the derivative of theta with respect to tau, the first order differential equation we were converging to. Now we have one-dimensional dynamical system that comes from a two-dimensional dynamical system. What happens with the information of the second variable? The information of the second variable, which is the value of omega at the beginning, is completely washed by the fact that even if these 2 points, initial points, are far away in phase space, basically they will collapse immediately to this one-dimensional problem. So effectively, your problem becomes one-dimensional. When? Under the conditions that I was describing before. So basically, the dimensionality of a dynamical system depends on your parameters. And many times when in the simple models that you're going to be describing in modern statistical mechanics, people are talking about very low dimensional dynamics because there is some reduction of the dimensionality given by the timescales of your problem. Okay, let's move beyond stationary points. I described so far one element of the description of a nonlinear problem, which are isolated points. Of course, you can have more interesting dynamics like oscillators. This in here is what is called a limit cycle. A limit cycle is an isolated periodic solution. What I'm talking about is that in our classical physics courses of mechanics or physics 1, we're typically involved with harmonic oscillators, for example. X dot equal y dot equal minus omega c square x. But that, what gives you, is a dense set of oscillations. Whatever initial condition you have, you will have an oscillation that goes, and passes by to this initial point. You can give any energy to a harmonic oscillator, and you're going to have a solution for that energy, okay? In these kind of systems, which are isolated periodic solutions, what you have is that there is only one solution which is attractive, okay? And the initial conditions, different initial conditions, eventually approach that initial solution. And in biology, that is typical. Your hearts are going very quietly, and then suddenly I look at you and ask you a question, then you're going to begin shaking a little bit. And then after a while, you go back to your transient of going to the same speed that you had before. So you relax to this oscillation, regardless of the perturbation that I give you, and those isolated solutions are called limit cycles. In terms of the elements that we had before, here we have a differential equation of a limit cycle. The derivative of the phase is a constant. So in terms of the phase, you are just monotonically, increasing your phase. But the values of the radius are described by this one-dimensional equation that we've seen in the class before. Let's see if we can work this out. I'm going to be writing R dot, that means R1 minus R, and this is R. So this is the vector field of the radial part of this equation. That means that I have a stationary solution at R equal to 0, and a stationary solution at R equal to 1. If R is positive, if R is between 0 and 1, R dot is going to be positive. if r is larger than 1, r dot is going to be negative. Therefore, your stationary solution for the radial part of the equation is r equal to 1 to be an attractor. That means that the phase homogeneously and monotonically increases, but r increases if small or decreases if it's large. This is what I was describing before, okay? You will have a solution of r equal to 1. This is r equal to 1. X, of course, is r cosine of theta. Y is r sine of theta. And then r equal 1 is a circle. And if r is smaller than 1, while theta monotonically increases, r approaches 1. And again, this is what happens if r is larger than 1. So far? And it's clear that it's isolated, right? In here, I have only one attractor. If I put an initial condition here, what will happen is that you will dissipate this energy, and you will end up with a smaller oscillation. It's not like in the harmonic oscillation that for any energy is conserved, and you have a solution that goes around and passes by this initial condition. And again, if you want to see something that is more recognizable, here you have an equation which dynamically is equivalent, but has a different vector field. That means that these equations are harder to recognize as the same. This is an oscillation where we recognize that this term and this term are what we would expect in a simple harmonic oscillation. But then you have a term that deals with the dissipation. That means that the dissipation is positive when x is large. Okay? So when x is large, you dissipate a lot. It's like, for example, if you're trying to oscillate between walls, and then you would reach a wall, you lose your energy, or you go back and you lose your energy. That's what this term is representing. And this is some energy that you're putting into the system. You're putting a term with the force that depends on the velocity. It's like when you're pushing a kid in a seesaw, right? In order to give energy to the system, you wait and you put force in the direction of the velocity, and then you transfer energy into your system. In order to make a system move, you have to put a force in the direction of the velocity. And this is what this term is doing. It's a negative dissipation. So in this system, what you're putting is, when x is small, you are putting energy. When x is large, you're losing it. And I don't have time to go over the detail of this. If someone wants to ask me about this, it's very nice to do the analysis of this problem. But basically, the dynamics is going to be an isolated limit cycle. And then we can put a little bit more together the concepts that we had. We can have a radial equation like the one we were describing before, but in the phase, we can put one of these differential equations that we were describing before. If r is equal to 1, we can have that the derivative is a function that can have zeros. So in this problem here, you are collapsing to this weird set, which is this couple of arcs which are connecting two fixed points. These fixed points correspond to r equal to 1, this goes to 0, and they correspond to the zeros of the sine square of theta, okay? So this is a 0, and this is a 0. These two guys are called connecting arcs. Why do I mention that? Because this is the typical idea of dynamical system theories, that is that you can geometrically show, and this is interesting for you guys coming from mathematics, you can show, for example, the Poincaré-Bendixson theorem, that if you have a region of phase space that is bounded, and your vector field is coming into there, you cannot have whatever you want. You can have a bounded set of dynamical elements, which are fixed points, connecting arcs, or limit cycles. And this is the flavor of what dynamics tells you, and this is the flavor of why people working in contemporary statistical mechanics like playing with toy models. Not because toy models are so great or because you have such a great intuition that your silly model, what you're saying, oh, this is a silly approximation, you are so magically intuitive that this is going to be pertinent. There is a whole theory that says that these simple models correspond to good approximations under a set of hypotheses because the set of possible dynamics that a nonlinear system can display are bounded, okay? So this is what validates the use of very simple models in modern statistical physics. So now, so for a given dimensionality, we have these dynamical states, solutions of equations that can be mapped to paradigmatic equations algorithmically. These are the normal forms, and those are the silly vector fields that we were describing. Very simple functions. So one question is, are these tools useful to describe real problems? And my suggestion is that for after the break, we go and literally ask birds. Because what I do is basically I started being an applied mathematician, by the way, and I late in life became a surgeon of birds and brains of birds. So I'm going to be talking a lot about biology and real experiments. So we're going to be testing simple models perceptually with birds. And my point will be to try to build confidence to you that these very normal forms, very silly models, very simple models, can be very accurate at describing very subtle concepts in real problems. So I'm going to close the first hour of my class in here, but before letting you go to the break, I'm going to ask for some questions. You won't go to the break unless I have at least 2 questions. Germán and the guys that I know from Buenos Aires, you can be my helpers at the beginning that were shy, because I need a couple of questions. Otherwise, Pablo, you will have to ask a question. So.
A silly question. How does this model connect to the easy model? Because they are very similar.
It is basically the hardcore of that. Exactly.
But in the easy model, we have two-body problems, right?
That's right. You have 2 states. So basically, this kind of model, what assumes is that you can forget about the transient, and instead of doing the description of the transient, you're just going to be making a description, exactly, where you have a final set of possible states. So if you wanted to, one thing that you could do is any problem that is stated in terms of Ising, try to describe it in terms of a continuous model, and then you will go to something like this. And what you will have is the additional dynamics of the transient that goes to what are the finite set of states in your Ising model. Exactly. So this is a very interesting question. Sometimes people reduce furthermore this dynamical systems approach and say, well, if I don't worry about the transients, what about just thinking that I have 2 possible states and I can be in here or in there, and claiming that the transition is not going to be important, make a discrete model that takes into account only the set of attractors of your system. But typically, this is a reduction that assumes, like in my problem of going to 2 dimensions to 1, it is the similar strategy in going in this problem in a continuous version to something with a discrete number of states. Yeah. Exactly. So what basically what the Poincaré-Bendixson theorem tells you is that if you have a bounded set, you can go to either a fixed point, an attractive fixed point, or a limit cycle, or some arrangement of arcs. Right. Beautiful question. So my plan would be to end my lecture today talking about how to classify larger dimensional systems. So let me give you the brief answer, because you deserve it. The answer is yes, you can classify dynamical systems, even if they have very complex dynamics. If you have, for example, strange attractors, you have families of strange attractors where the topology of the solutions are qualitatively different. And you can classify systems, even chaotic, because of the topological organization of their periodic solutions. You can have families like this, the family of the Smale system of flows, the Lorentz systems of flows, and so on. And then the topological organization of the periodic solutions will be qualitatively different, and you can classify them as well. So yes, although it becomes further complex the higher the dimensionality of the phase space is, of course. I was about to have another question. Yes.
When adding like stationary points to the phase information of the system, what kind of application does it have? Does it makes it easier to model like complex frequency and resonators in the spectral space?
Typically, when you have more a larger number of fixed points. Typically, that happens because you had to go to a vector field with higher nonlinearity. And a higher nonlinearity usually won't appear unless you have a symmetry that requires it. So for example, the larger the symmetry, then the larger the degeneracy that your vector field will have. For example, in this case, you went to a cubic term when you have the picture bifurcation because you had a symmetry that didn't allow the zero-order term or the quadratic term. So why would some higher nonlinearity appear? Typically, it will appear generically only if the system is bounded by some symmetry. So for example, if I have a D4 symmetry, then typically I will have at least 4 fixed points, or things like that. So it is usually the leftover of some symmetry that either you wanted to put into your system or you inadvertently included in your system. And you have to be very careful about that, because if you put a symmetry into a problem, typically then what you are describing is the symmetry itself and not the problem. If you have a convection problem and you put it in a square, and then you start to look at the patterns, no? If you do a convection experiment and you put a square, and then you look at the small aspect ratio problem, then you see after the conduction, you have conductive state. You have cold lines where the fluid goes down and so on. And then you increase the temperature, and then what you have is that you go either to this pattern or this pattern and so on. Then you're not studying convection. You are not studying Navier-Stokes equations. You are studying the symmetries of a problem with a square symmetry. So you have to be careful when you have a large number of fixed points. Typically is that you are using a dynamical system which has some symmetry, and you want to be sure that you wanted to put this symmetry because it reflects something really in your problem, and not because, I don't know, you were lazy enough to do something that looked simple, and then you filled it with symmetries which were not pertinent for your problem. Okay? So what about going for a half an hour break, and then we meet for the second class?